going to tell us about topological phase transition. So whenever you're ready, the floor is yours.
Okay. Good afternoon, everyone. So thanks for the introduction. First of all, I'd like to thank the organizer for the opportunity to give this talk here. Although I put topological phase transition strain Lieb-Kagome lattice as the title of my talk, actually, I go beyond that. This is one of the topics that I will discuss with you today. First, I discuss the effect of strain in these two lattices. After that, we go to the topological phase transitions. After that, I will say I will discuss few results on nanoribbons of those kinds of lattices. Also, investigate the thermodynamic properties of those lattices. I will try, okay? And talk about multi-layer. We expand our theoretical model proposed in 2019 for monolayer to multi-layer case, and also discuss just a little about symmetry analysis, okay? So just to tell about the group where I make part. So this is led by Professor Gil, and all the rest, it's a member of the group, Professor Andrei, Raimundo, François Peters is a visiting professor, Professor Jean-Lex, Professor Milton, and me. So here it's the students that who do the hard work, okay? If you want to know a little more about the works that I had developed, and I'm still working on different types of, different areas, just point your cell phone and take a picture of that, okay? Okay, so let's first introduce these two kind of lattices, Lieb and Kagome, okay? Both share some crystallographic and electronic features. For instance, both are composed for 3 atoms per unit cell. Both lattices has their spectrum with the coexistence of a Diercke cone and a flat band. And I know that Rodrigo later talk more about realizations of Lieb lattice, and take a picture and show to Christian. You see, they are cited our work. And this Lieb and even transition, I'm going to talk a little more. In Kagome, they can realize in photonic crystals, organic analogues, and so on. And each of those lattices present different physical features. For instance, I've just point a couple of them, enumerate a couple of them. For instance, if you apply perpendicular electric field, the way that the response is different. You can see for the B field profile of the energy, and even the Hofstadter butterfly of these two lattices has a different shape. And both of those lattices is pseudo-spin 1, and when you compare with pseudo-spin half, like graphene that has a Klein tunnel effect, now you have a super Klein tunnel that corresponds the case when the incident electron has has energy that is half of the barrier high. You see the barrier as a transparent, okay? So the probability of be transmitted is 100. So, and a natural question arises. So, since that these two lattices share crystallographic aspects and some electronic aspects, so these two lattices are somehow connected. And I have to say that it's the main motivation for all the works that I present here today is because yes. And it was shown in 2019 by the group of Professor Tony Lowe. I met this postdoc in the time, who show based on group theory that these two lattices are interconvertibility. It means that if you apply some diagonal deformation, you can map all the evolutionary stages between Lieb and Kagome. And they proposed a very simple model based on a single orbital and one parameter tight-by model. And the way that they propose is not put by hand. I have to say that 1 year later, different groups, especially this one, they pretty much did the same, but they changed by hand the coupling between the next year's neighborhood, okay? Different from the Ways paper, where they propose a model and show that based on group theory that Lieb that belongs to the D for age merged to the D6 age group. And one more example that it can be realized, even this transition lattice between Lieb and Kagome, this paper show some interference pattern in a photonic crystal of a transition lattice. So it's not things that theory likes to play with the morphing between the two lattices, but in practice, they can be realized, okay? So, and how is this model that they propose? How to deal with this interconvention process? So, as at the beginning of any crystal that you are working, you first need to write the lattice vector. So here are the two lattice vector in the real space, and you see the dependence on theta. And theta is this angle between the where I connect AB and BC, okay? And since that one of the works I will apply strain, I also put already in my model the deformation that comes here, that is the displacement vector, okay? And can be written in terms of the strain tensor, okay? At the end of the day, you can write like that. In reciprocal space, so you go to have a morphology between square-like first Brillouin zone to hexagonal first Brillouin zone. And here we have our B as a function of theta, and we can calculate the high symmetry points, again as a function of theta, and also any point in the reciprocal space if you deform your real space. Okay, and since that I'm deal with 2D Lieb-Kagome lattice, so we use the 2x2 strain tensor, where this guy here is the Poisson ratio, and the epsilon ij is connected to the formation direction, and which sublattice will, which component will be applied, okay? So here it's the full form of any point in your real space, how does it be transformed? So I apply 6 types of strain to see how the electronic properties change when you apply, for instance, uniaxial strain along x and y direction, biaxial strain, simple shear strain along x and y, and pure shear strain, okay? This is done just replacing this 0 and epsilon in our matrix. And here it's just a beautiful illustration how you can see this Lieb and Kagome lattice deformer. Okay, and as I told you, we use a simple tight-by model, and here it's written with the creation and annihilation operators for one electron and sublattice A, B, and C. Here is the on-site contribution. Here is the one that deal with the hopings. If you written a base and a Fourier basis, you can bring your Hamiltonian to a reciprocal space, and you can calculate these structure factors, knowing the position of the first nearest neighbor, second nearest neighbor, and third nearest neighbor. And we end of the day with this 3x3 matrix, and here are the structure factors. Up to this point, I didn't mention nothing about how those hopings are treated. So to be more general as possible, we consider a position-dependent hoping, okay? Like that. And this and here plays an important role in our model, because since that in the limit case for the Lieb and Kagome, you want to capture the flat bands. So we play with this guy to see which one is more convenient. And we plot the hopings as a function of the distance for different ends, and seeing the first and the second nearest neighbor hopings, and noting that this one is the first nearest, and here's the next nearest. You can see that if you take, like, as we go to choose n equal to 8, for transition lattice, it has a no significant contribution for second year's neighbors. What I mean with that, I just go back few slides, just to emphasize for you that in this morphing, some first year's neighbor for Lieb lattice, you become second year's neighbor. It's why this will be important to carefully look at. And for any stage, the third year's neighbor is neglected. And as you increase the number of n, you're hoping decay fast. And here is the energy spectrum for this Lieb transition for a fixed angle and Kagome lattice. And once that you want to capture back the relation, the special relation where the band is flat, so we go to choose n equal to 8 from here until the rest of my presentation, okay? So let's just talk some interesting stuffs about those energy spectrums. So in the morphing, you can see that for Lieb lattice, you have a triple degenerate point at M that splits in two type 1 and 2 tidal Dirac cones until it just be one double degenerate, just one Dirac with the flat band go down. It can be down or up depending on the value of the hope, if it's positive or negative. So I want to emphasize that during this morphing, there is no gap open. And here I just zoom in for you that to show you that during this morphing, you get a double, two Dirac cones, okay? Type 1 and type 2. So once that we put in the same page about this lattice, let's talk about a little about the effect of strain on those Lieb and Kagome lattice. So I move directly to the results. So when I apply uniaxial strain, it will be a lot of plots. Sorry for that, and I need to move fast. Always I put the reference 1, the 0, without any strain. And here is along x direction, and here x and y direction. As you can see, you apply uniaxial strain, you get a triple degenerated Dirac state, as here. And to emphasize that, I show a 3D plot by increasing the strain amplitude. You see that these two Dirac cones approach and get close, close, close until it get a triple degenerate Dirac line. Moreover, I can say that during this morphing, the isotropic Dirac cone get an anisotropy. It means that it will be a strong impact in transport properties, since that the group velocity, you depend on the direction, okay? Moving to the biaxial strain for the Lieb case, it's simple to think that if you apply a combination of uniaxial strain in the x and y direction, your lattice will deform equally. In the sense, your energy spectrum will keep the aspect ratio. So if you increase in the real space, you decrease in the reciprocal one. It's why by extending your real lattice, the area of the first Brillouin zone decrease, okay? But it's nothing more surprisingly happen here, okay? Now the picture is completely different if you go to shear strain. For the shear strain, the the triple degenerate hierarchy point for the Lieb case split in in a pair of two double degenerate cones at the M point. And I want to say that that paper that did by hand just changed the hopings. I mean, they didn't apply strain. They just changed the hopings by hand. But keep in mind that change the distance, you change the hoping. And so in principle, we did similar stuffs, and they found it. They found a similar thing. For the Libby, they found those just changed the hoping. For the second year's neighbor, they also found those the splitting for the two hierarchy cones. And for pure shear strain, it's like a combination of the two shear strain, but now all the spectrum is tightened. I mean, all the spectrum is twisted, okay? Now let's move for Kagome. And Kagome, most of the results for uniaxial strain resemble those for graphene. And for those that are familiar, this is the Castro Neto paper. And they show that this cone started to get close and close. But in graphene case, applied uniaxial strain, open a gap. In Kagome, no. There is no one of those 6 type of strain that I apply open a gap. And moreover, due to the interconversibility between Lieb and Kagome, as I discussed at the beginning, my main motivation, it's easy to think that probably there is some type of strain. If you apply in Lieb, you get some similar if you apply other type of strain in Kagome. And for instance, just to enumerate, if you compress, apply uniaxial strain in Kagome lattice, you pretty much get the same as a shear strain along x direction for the Lieb lattice. And for biaxial strain, there is nothing too exciting except for the fact that your flat band, that is this one, it gets less. I mean, if you compare the color bar, you go to realize that the dispersion of this quasi-flat band is become less and less dispersive. Okay. And moreover, you can see that it's shifted in the spectrum. And to understand that, we fit it, and of course, since that our hoping has an exponential dependent, also here you get some exponential dependent. And when we plot the energy as a function of the hoping, it gets the very conventional hoping, very conventional energy for the flat band. It's 2 minus 2t, but just replace t for t prime. So, and for the shear strain, they are mirror image for positive and negative deformation. And there is a bunch of stuff, details that I can discuss, but my time does not allow me to do that. And the same for pure, it's just a combination. But now I have to emphasize that during the morphing, it's really strange how the first Brillouin zone moves to a hexagonal to like a parallelogram. Okay, so for this first part of, I want to say that no type of strain open a gap, and for uniaxial strain along x and y and biaxial strain for the Lieb case, you have a split of the triple degenerate point, breaking this degeneracy, to two double degenerate Dirac cones. Okay? So we published this in 2023. Here it's key accord if you want it. And let's move to the second one. That is the title of my presentation itself. So I choose to first show the effect of strain, since that in this paper that it's submitted to PRB, we review what is in literature when you take into account spin-orbit coupling, but also you apply strain, okay? So, to 8 minutes. It is. Yes. So the way to include this is like that here. I just add this term, and this E sorry, this guy here, you minus plus 1, depending if it's clockwise or anti-clockwise. Here it's the sigma, it's the Pauli matrices. And we took a very similar exponential dependent for the spin-orbit coupling. I have to emphasize here that some papers in literature just take into account next near neighbor for the spin-orbit coupling. Others take both. And once that the interconversibility between Lieb and Kagome, we just discussed that some first year's neighbors become second year's neighbors. To be consistent, I assume all the situation. And in this paper, that is quite long paper, we compare with the stuff that is seen in literature and find new ones. Okay? So I just jump that, you know that. Just expand in Fourier, and you can write our Hamiltonian in K-space. Here is the, without spin-orbit coupling, you just add this guy here, okay? And since that we didn't apply magnetic field, and we are keeping time reversal symmetry and inverse symmetry, so it means that all the spectrum that I go to show you is spin degenerate, okay? And to characterize our topological phase transition, I calculate the chair number, the Berry curvature, and see the situation where you have a close and reopen the gap, okay? So let's go. So in general, if you take into account spin-orbit coupling as expected, it open a gap for all the case. And here I plot situations where I take into account first, next and near next neighbor for the spin-orbit coupling, and just second year's neighbor. But I have to say that in case that you just take nearest neighbor, the Lieb lattice, when you take into account spin-orbit coupling, does not open a gap. And it's because it keeps the D4H symmetry. And we started to play with the different lattices, the different couplings, and also the strain. But even let's start with this one. First, I want to point out some interesting features. Like in the case that you just have second year's neighbor, is what the literature most of the time discuss. Your Berry curvature are symmetric, and the flat band for the Lieb case does not have any contribution for the Berry curvature. If you take the same situation concerning the spin-orbit coupling, but now for the transition, your Berry curvature is anisotropic, and moreover, you get a Berry dipole. Also, for this case here, the case that you take into account first and second year's neighbor for the spin-orbit coupling, you also get this Berry dipole. Generally speaking, for all the cases that you have both the sign of the Berry curvature per band does not change, as well the chair number per band does not change. But the picture is different when you take just the second year's neighbor, that is this case here. And if you compare the sign of the Berry curvature, like here is positive and here is negative. So it's indicate that has a topological phase transition. It's one feature that has indication there's a topological phase. So with that in mind, we will do some contouring plot, change different parameters, like the one that controls the hope and the one that controls the morphology. And as you can see here, for n equal to 8, that's the one that captures flat bands, you see that it's open, close, and open again. Moreover, I did for all the different type of strain. And I did this analysis systematically. And you see situation like, I can point like this one, that it's, see that blue, it's close. Close, open, close. So one case of that, and if you go to the Berry curvature, you go to see the sign difference. And also you go to the chair number, you go to see that the chair number change. So we map different case of when you apply strain and you tune the spin-orbit coupling that have topological phase transition. You did different kinds of phase transition that my time does not allow me to discuss on that. So with that, I just say that we post this on archive. It's in archive. So just a few words about this in 3 minutes. I promise that I discuss these 4 works. So since that our motivation is the morphology, it's what happened between Lieb and Kagome lattice. So we started to play with different systems. For instance, let's see nanoribbons, the edge effect. We treated different types of edge, straight, beard, and asymmetric. And in this paper that's already published, so we discuss about the degeneracy of the quasi-flat bands when edge states emerge. And at the end of the day, we did for Lieb, Kagome, and transition. And at the end of the day, I want to say that what at the beginning for me, at least for me, when I started to calculate that, I thought that those guys here, it would be like, you behave like those flat bands that just took sublattice as equal contribution, but it's not the case. When you take a nanoribbon, those guys here, the behavior of the probability distribution, it's like in the book that has a nodal behavior. And moreover, just Kagome has edge states. Okay, this is a... Yes, for sure. Those one, it's, this is the probability density. And in the real space, and here it's a cross-section. Those guys here are a cross-section of that. Because I just took a print screen and put here, the quality is not so good, but it's... Okay. But see here that is the edge stage, just localized at the edge. And so you also, this is one of the last one of these papers that we are finished, and we calculate some thermodynamic properties like heat, specific heat, and paramagnetic susceptibility, and see how the behavior of those quantities are in the morphological stage between Lieb and Kagome. And you consider Zima and also spin-orbit coupling. So since that I have 30 seconds, I just move. And also we extend this proposed theoretical model for the multi-layer case, and like a three-diagonal block matrix, consider AA and AB. And generally speaking, we saw that for AA case is just copy of the monolayer as AA bilayer graphene, but the picture is completely different when you take AB due to the no symmetric symmetry, and especially here for see Lieb that those bands here are degenerate along X and M. So this is also in archive and was just accepted in nanotechnology. And the last one, my time is up. So we analyzed this accepted paper in the sense of group theory. So yeah, my student did a very hard work on that. It's beyond my knowledge, most of those stuffs. And that's all. Thanks for your attention. And
okay, thank you for the talk. So, questions?
So I have a question about the first part of the talk when you include strains. So the conclusion is that you are not going to gap out, right?
no one of the lattice.
Right, but do you understand why in terms of symmetry arguments? Because in principle, if you put strain, you reduce the symmetry group gets smaller, the symmetry gets reduced, and then in principle, you can allow for mass terms. So why don't you never, why doesn't it never happen?
Yeah, in some case, we try to understand, and we wrote that in the paper, but what I have to say for now, as far as I remember, that you have to break the null equivalence between A and C sublattice. This is the one that open gaps. For instance, if you take a sublat break symmetry, I mean, if you take a substrate as induce on-site energy just in B sublattice, this will open a gap. So for sure, some symmetry is reduced, but I don't know. We didn't analyze this in time.
Okay, thanks.
More questions?
Thank you for the talk. I also have a question regarding the first part. So you showed these hoppings that are not uniform, and you had this dependence on n, right? And so in the material, how would we control that, for instance?
I mean, the material, it is what it is. I mean, but here, since it's a toy model, we can choose the value that we want. And our argument, the same as the one that the original paper from 2019, is to try to recover the flat bands. What is the n that recovers the flat bands? It's n greater than 8.
Okay, thank you.
Okay.
Anyone last question? Okay, so let's thank the speaker again.
Okay.